So, what do we do if those things don't apply? Well, there's another trial-based algorithm that functions slightly different. And we tend to use this if it's too expensive or difficult to enumerate all the states reachable from or all successor states. Right, so this is, if it's difficult to enumerate all of SAS prime, so if the kind of number of those is very big, or, and this is a really important use case, we don't have this explicit transition function, right? So we don't have T. But what we can do is we can simulate, or sometimes you can just think of it as sample, the transitions. So what do I mean by simulate the transitions? Well, in the previous example, we sampled an outcome, right? From, let's say we had, our successor state was a coin, and I had written down in my computer code, probability of heads equals 0.5, probability of tails equals 0.5. And then I'd ask that random variable, sample me an outcome. And then it would tell me heads or tails with equal probability. And I could run that sampling repeatedly. But if we think about the poker example, and I want to think about, well, what would my opponent bet if I bet 100 chips on this card? I don't have the probabilities written down anywhere. But what I might do is I might have another process that I can run which actually simulates the outcomes of that action. So maybe I've got a kind of simpler poker playing simulation in my head that I can run to imagine or kind of hypothesize, hallucinate the outcome that you might come back with, the opponent might come back with. And I can do that for different actions, and I can do that and get different outcomes back. And there are many robotics problems like that, where I have a simulator or some other kind of stochastic model of some part of the problem, and I can run that to draw a sample, but I can't ask it for the actual probability. So there are poker, manipulation of structures in the world, interacting with humans. Typically, these things are very hard to capture in an explicit transition function, but are easier to have some kind of simulator or model for. And so what we're going to do now is we're going to look at algorithms that use that kind of sample-based representation. And in particular, we're going to look at something called Monte Carlo tree search. So Monte Carlo tree search moves away from needing to know the model and does sampling and uses the results of sampling, so the sampling statistics, in order to compute in order to compute action choices. We can run this online or offline, like RTDP. And in certain situations, we can know how good or bad our actions are. So the nice thing about RTDP is it's optimal given enough time, because we're using the true model. Monte Carlo tree search, or MCTS, we can only really say that with high probability, we're within a certain percentage of the optimal action. So our action is pretty good. But when your problems are so big and difficult, that's typically all you can do anyway. And it's another algorithm that in the limit, if I give it infinite samples and under kind of mild restrictions, then if I do that, then I can get the optimal solution back. Okay. Before we move on to looking at this algorithm, does anyone have any questions on the distinction between when I would use this and when I would use RTDP? Or the difference between having an explicit transition function and a simulator? Sometimes we'd call it a black box simulator because I can't see how it works. It just gives me the outcomes back. Does anyone want to ask questions there? Okay. Now this algorithm has been quite popular recently because DeepMind's AlphaGo system, AlphaZero, a lot of these kind of fancy new AI game playing systems use MCTS to choose their next actions. So the kind of learning community and the game playing community has really used this algorithm as a kind of key workhorse in their software stacks. So the key thing we need to do now is compute these Q functions again. And here, rather than having this table of values and models, we're simply going to use rollouts or trials through the model. So it's going to be very similar to actually how RTDP worked in that respect. We start at some state, we select an action, we sample the action. And now at this point, we just start to accumulate the cost. So in each state, we can keep track of how much cost we've got. And we roll out this model until we reach the end. And then when we reach the end of the model, the end of our rollout, so this is typically called a rollout, because we've rolled out our model, we can use the total cost of that to approximate the value of the initial state. And here what we're going to do is kind of throw away the Bellman equation to some extent, and we're going to use some other selection process, and we'll talk about this a bit more when we get onto reinforcement learning. The key question here is how do we choose what action to use in our rollouts? And this is a bit trickier than before, because in RTDP, we use the model and the heuristic to choose actions which were approximations to the greedy policy. Right? Our heuristic told us roughly which actions looked good, and then those approximations got better as we ran the algorithm. In Monte Carlo tree search, we don't have a heuristic, and we don't have the model to accurately estimate the value of the actions. So instead, we need to interleave two different types of choices. We need to do what's called exploration, which is choosing actions that we don't know very much about, and exploitation, which means choosing actions which we know are good. And we will revisit this in about an hour when we come on to another algorithm. But we balance this in Monte Carlo tree search by using an action rule called upper confidence bound for tree, UCT. And the UCT formula is down there at the bottom. So we're still minimizing some Q value. Okay, so that here means, in fact, it's sample-based. But what we're also doing is we're subtracting this term here. So this is the UCB term. And what it's doing is it's making actions that we haven't taken look a bit cheaper. So this is how we balance exploration and exploitation. We look at the Q values, and then effectively actions that we haven't chosen very often, what we do is we make them look even cheaper using this constant times a function of the number of times we visited them. So this is a way of sort of biasing the action selection to do a bit of exploration. Okay. So the algorithm looks a bit like this. Although actually the algorithm here is longer than RTDP, it's really simple. It's actually much simpler to implement than RTDP. And it can be done really in a few lines. It's not a hard algorithm to get your head around. And it's a bit easier actually just to go through the an example rather than talk about the algorithm. There are 4 steps which we run through. We repeatedly select and expand. When we reach a state that we haven't seen previously, we then create an initial estimate for that node using a rollout. And then when we finish our rollout, so typically when our rollout reaches the goal or we reach the end of our tree, we back propagate our values back to the tree. And then we start selection again. So if we look at this, we're going to build a kind of tree-based example that we saw before. So I'm going to draw things like this, which are going to have the structure action, Q value, and now we need to keep track of the visit counts. Okay, so now we need to see N is going to be how many times have we tried this action in this state. And that's what we need to do to keep track of the sample statistics that we saw earlier. Okay. So in this algorithm, we have 2 types of search nodes: decision nodes and chance nodes. So the decision nodes are going to be circles. Sorry, this whole slide just rendered in the wrong order. Give me 1 second. Just want to write that down. The circles are going to be decision nodes. So these are nodes in which we need to choose an action, and they typically correspond to states. Okay, so we've got our state S, we've got the value of the state, and we've got the number of times we visited it. So here, for example, state D, an estimate of its value 8, and we visited it 4 times. So these correspond to states, and they're the location, the places in the tree that we have to choose, hence we call them decision nodes. Chance nodes show the action we've chosen, right? So the A for the action we've chosen. And they're chance nodes because at these nodes we sample an outcome. And that sampling is governed by chance. So it's after this that we call our simulator. Right, let's see an example. So we'll run this on the same example as we did before. So we've got our initial state D. So once again, we need an initial state here. We know nothing about D. We've got no heuristic, nothing like that. So the key part here is we haven't seen this node before. We haven't seen this node before, so we know nothing about it. We haven't seen the node before. We have to choose the action. And in this case, because we know nothing about it, we've never seen this state before, we're going to be forced to choose all actions once. Because that's going to allow us to at least compute those minimizations over the action. So we're going to be forced to choose all actions once. And it can be a random choice the first time. So here we haven't chosen E. So we're in state D. We haven't chosen A or E. So we choose E. Then we sample a successor, right? So just like before, we're in D, we've chosen the action of going to E, and there are two possible outcomes. Either we stay in D or we get to E. So in this case, we sample a successor, we have an action cost of 2, and it ends us up in D again. And because we haven't seen D before, we're going to perform a rollout to estimate the cost. So there are different ways of doing these rollouts, but what we can assume is the rollout is like a random walk where we sample random actions and then random outcomes through our MDP. So it's still a sample-based process. And so here what we're going to do is we're going to estimate the value of state D, in this case D2, because it's the second time we visited D. And we do that by estimating the cost to get to the goal. So by running that sample, you can see we're choosing some random actions. So we're in D, we chose to get to A, we chose to go to A, we chose to go to B, we go to C. That can all be random. We sum the costs to give us a cost of 5, which we can put into here. And then we can back that up here, which allows us to update our Q estimate. So if you look here, we'll just step through this again. Forced to choose this action, sample a successor, so these kind of sort of purple arrows are samples. Reach a state we've not seen before, which is D further down the tree. We perform a rollout to update the value. And then we use this value, 5 of the state plus the action cost of 2, to update the Q value in the tree. We've tried this action in this state once, so we update this to 1. And then we can back up our Q values to our root node D, which is going to be a value of 7. That's one trial of MCTS. And now we repeat it. So because we haven't chosen all actions here, we have to choose another action. And this is typically going to be the case in RTDP2. So although we didn't see this in LRTDP, this is happening in LRTDP. You always, if you want to choose a min or a max over a set of actions, you typically have to have tried all the actions first. But the nice thing in RTDP is because we've got a heuristic, we don't actually have to do any processing. So we've kind of enumerated the actions, but we've used the heuristic. Here in MCTS, we have to actually do a little bit of work before we can decide which action looks best. So now we're at D again, trial 2. Well, we haven't tried the action of going to A. So we try that, so that adds a chance node. We sample an outcome. So that outcome cost us 2 because we performed an action of cost 2. And we end up in state A. Well, we haven't been in state A before, so we run our random rollout to update our estimate. Okay, and that gives us a value of 3. Now we back up 3 plus 2 into 5 in this node. Update n to 1. And now we need to back up our value to D. At this point, we can minimize over the 2 actions. So going to A is cheaper. So we run our backup, which is computing our value estimate for that state. We're minimizing over the actions. We're allowed to do that now we've seen all the actions that are available. I'm going to keep going in a minute and show you what happens as the tree grows a bit bigger. But before we do that, does anyone have any questions or need a clarification of what's going on?
Hello, sir. Can you go back to the last slide? I have a question about the trial 1.
Trial 1, yeah.
Yeah. Why not do we have successors state just from E to B to C instead of D to A to B to C?
So this is this bit down here is a random rollout. So because I've not seen D before, and in fact there's a bit of subtlety here, which is in MCTS I'm going to think about states plus the levels they are in the tree, because D in the root position is actually a different state from D in the next position. But we don't need to worry too much about that. What I need to do is I need to estimate the value of D. And because I haven't got a heuristic, I need to come up with some way of estimating that value. So the basic way to do it is to say, well, let's imagine I've got a random policy. That random policy just chooses a random action in any state. And I run that random policy until I reach the goal. So what that does, it chooses a random action in D, which is to go to A. And then it's in A, it chooses a random action, which is to go to B, and then it chooses a random action, which is to go to C. So it could have chosen any path here that's valid, and it would terminate when it reaches the goal. But this is a kind of Monte Carlo sample. It's a random sample, and we're going to use these things to approximate the costs that we're going to expect to see. So the answer for why this particular... Oh, yeah, go ahead.
Oh, yeah. So there's also possibilities that the successor state will be E, but just we're not listed here for the trial one.
Mm-hmm. Yeah, it could have been any trajectory that reaches, but it's randomly sampled, so I can't control that. And this example was actually, I ran an implementation and just copied the implementation into my slides. So this was kind of the real choice that a computer program made, or a real random selection.
Okay, thanks.
Okay.
So it could be that we go from D to E to F to C. Is it like that? Since it's random, so D to E to F to C.
Yeah, that could have happened.
Okay, thanks.
Or we could have gone from D to E to B to E to B to E to B to C, right? We could. There's no smart.
All right.
Yeah, the idea here is statistically, this is giving us some kind of unbiased estimate of V. So it's trying to estimate the value, and we're going to do it in a sample-based fashion. But it just has to give us anything, and we tend to use the random rollout because it's simple.
Okay, but is it possible that, okay, say for example, I'm from here D to E to C to B and come back to A and D, like could it be possible like that? Oh, the doors are other way open, sorry. Now it's not possible.
Yeah, it has to follow. It has to be a valid sample.
All right.
And if we hit C, we terminate because it's the goal. Right?
Okay.
So Charlotte in the chat asks, so in different simulation trials, the values are different. Yes, that's correct, right? So if I get to D and run another rollout, I might get another value. And then she asks, so do we need to take an average? And the answer is yes. That's exactly the way this is going to work. So the only thing we can do, because we don't have a model, is that we're going to use averaging. But the fact that the samples follow the distributions will mean that that average tends to the expectation over time. So that's the whole idea of MCTS, and that's what we'll look at in a minute. So as we run samples, we take the average, that average, because it's being generated from a simulator that respects that kind of encodes the probabilities, that's going to give us the expected values correctly. So yeah, it's a good question, and we'll see that in a minute. So trial 2, as I said, we have to choose all actions once, and that can be a real pain, and there are kind of extensions to get beyond that. So what we'll do is we can sample a successor here again. We run a rollout. These rollouts being very friendly to us. We back up, then we take the backup there. Move on to trial 3. And at this point, we need to make a choice. So here, we're going to use the UCT rule that we saw. And we're going to compute values for A, DA, and DE. And then we choose the minimizing action. So if you remember, the UCT rule looks at the cost or the Q value, and then weights that Q value based on the number of times we visited the states. In this case, actually, the number of visits is the same. And so the difference between these two is actually 2, which is the difference in costs. Right, so A looks like a better action because it's 2 cheaper than E, and it's had the same number of visits. So UCT isn't doing very much for us there. We sample a successor, and let's say, well, we end up in A again. Hang on, what do we have for? Yeah, we end up in A again. Now we've seen A once before, we're allowed to incorporate it in our tree. So what I'm doing here is green nodes are things we've only seen through rollouts, and they turn white when we're allowed to keep them in the tree. So now we're going to expand. We've seen it once before, so we're allowed to expand. And we have to go through this process of forcing an action choice. So we have to explore all actions from A. Luckily, there's only one. So what we do is we take that action. That takes us AB. We sample an outcome. That ends in A2. We draw a rollout. And this time, our rollout is awful. And again, this is a real rollout on a real system. So we take our random choice and we go B, E, F, E, B, E, B, E, F, E, F, C. And so we're going to throw in the estimate cost of A. As 14. So what's happened here, right? We're in A, we tried to get to B. That action threw us back into A. That we know should be a kind of a 0.3 probability. So now we have to estimate the value of A at a second visit. Gives us this really bad rollout. We back that up through the tree. And now what we need to do is we need to compute the Q values using these averages. Because once we get back up to D, what we've got is 2 different values. Okay, so let's just think about this again. We get down here, we get our value for A here. We push that value back up the tree like we did before. But now we get to this node, which has got a value of 5 in it already. And we want to update the value here. Well, we're going to use that by taking effectively the average. So we've got our Q value, so the formula's here. And basically it's going to just take the average that takes the previous average, adds on the difference, and divides it by the total. So this is simply just taking a running average. Right? It takes the old Q value, adds on the new value, and divides it by 2. So we've got 518 divided by 2. That gives us a new value of 11.5. We update that Q value. We update N. And then we can update. So here we update the value of D to 7 because now the best action is E. So the key thing that we saw in this slide is this averaging. So this is the averaging that Charlotte asked about. Effectively, every time we update one of these square boxes, one of these boxes, we use the average of the return we've just seen from our trial, averaged with the previous value we saw there. And this is going to allow us to manage over time, this should converge to close to the true value. But of course, in the short term, as we get these kind of big random samples, it's going to throw these estimates all over the place. Okay, so the key point here is that as we run trials, we're gonna just take the average of all of the trials we've seen so far to update the action choices. All right, questions?
Well, Professor, here I do see that in iteration, this BE. Well, why it's repeating though like that?
It's random, right? It's just that's a random rollout.
Okay.
So there is no Y.
Okay.
The Y is it hasn't reached the goal. It just chooses a random action.
Okay.
And that's what random.
This was something I was saying earlier. Okay, now it makes sense to me. Thank you.
Okay. Any other questions? Okay. So next trial 4. Oh, chat message. So Charlotte says, so do we get a stable value during iteration? In the limit, yes. As you can see, at the moment, our numbers are jumping around a lot. But once you start drawing more samples, you start to converge to something more stable. So yes, in the limit, so as kind of with infinite numbers of samples, we get stable values. Right, trial 4. Now we're going to choose to go down this route because now this looks a lot cheaper. It looks a lot cheaper because we've visited it one time fewer and because the Q value is lower. Sample and outcome. Well, here we sample E. We take a rollout. Again, it's not a particularly great one. Cost of 7. We back up again, we back up the values. Those values are incorrect. There should be a 7 there, not a 5. Why are these slides buggy? We back up. We now average this to 8 and update to 2. We roll again. Choose the right-hand side, the action's still cheaper. Now we hit E for a second time, we're allowed to expand it. So we force an action choice of F. We sample a successor, we roll out, we back it up, and compute our new estimate. That makes that cheaper again. So now you can sort of see we've washed out the effect of that expensive rollout before. Oh, that was the same trial. And what you should be able to see is that over time, as we do this again and again, the statistics in the nodes will get more accurate. As we build the tree, we're removing the results of the random rollouts as we build the tree. And we get more accurate estimates. And if you look on the right, so this is from an implementation of this algorithm on the sort of 6-room problem. And you can see that the value of the initial state, this is the value at D. So this is the value of being in D, which is effectively the value of the optimal policy. And we know from our previous use of value iteration that the optimal value is 4 point something, I think, 4.8 maybe. And you can see with Monte Carlo tree search to start with, we get a very bad estimate of that value. But over time that value converges. And so this shows you that over time, this number of trials we get closer to the true value. And the advantage here is that this algorithm, typically a single trial is quicker than a trial of RTDP. And we don't need to actually have the transition function in an explicit form. Okay, and what I've shown you with the sort of example is just roughly how you build up those values in the tree. Okay. Right. I think that's all I wanted to say about that. Any questions on Monte Carlo tree search? I think the important thing to think about is this is really just using averaging. And if you've ever done any averaging on kind of data, you know that the more samples you've got, the more data you've got, the better that average and the more accurate the average. And that's really what this is doing. It's just kind of sampling through the tree and giving you data to compute averages from. And the more time I've got, the more samples I draw, the better my average. So, given infinite time or infinite data, we can get the true optimal A. And we can repeatedly run this over time, which is quite nice. We can keep the data in the tree. And so we can run it online quite often as well.